Hello, welcome to the course SJPHY1C01 Properties of Matter and Thermodynamics. The contents of today's lecture is taken from Heat and Thermodynamics by Brijlal and Subramaniam. We will continue to discuss topics from Module 3, Thermodynamics. In the last class, I have mentioned about Carnot Engine, which is the ideal heat engine with maximum efficiency. So as I have explained, it has four major components. One, a cylinder with ideal gas inside. The walls of the cylinder as well as the piston are non-conducting. On the other hand, the base is conducting. And there is a source at constant high temperature T1 and sink at constant low temperature T2. The walls of source and sink are non-conducting, but the top side is conducting. And there is an insulating stand. Now, in order to get continuous supply of work, the working substance, which is the ideal gas, is subjected to a cycle of quasi-static operation, and this is known as Carnot cycle. And Carnot cycle consists of four major processes: two expansions and two compressions. First one is isothermal expansion, then adiabatic expansion, third one is isothermal compression, and finally adiabatic compression. So it's a series of expansions and compressions. Let's first look into the first process, isothermal expansion. So here the cylinder is placed on top of the source. So remember, source is at a high temperature T1, and the top side of the source and the bottom side of the cylinder both are conducting. So what happens? Heat flows from source to the cylinder and the working substance acquires the temperature T1. Source has infinite thermal capacity, so how much our heat flows from it, the temperature doesn't change. Okay. So when the working substance reaches the temperature T1, what happens? Temperature is high, so the gas expands. So if you look at the indicator diagram, the volume is going to increase from V1 to V2. When volume increases, what happens? The piston is going to move upward. Consequently, the pressure is going to decrease. Pressure decreases from P1 to P2. Okay. Now, when the volume increases, there is a tendency to decrease the temperature, but there is continuous supply of heat from the source. So because of this, the temperature remains constant at T1. So we have an isothermal expansion happening at temperature T1. So if you imagine that the working substance changes from initial state A, characterized by coordinates P1, V1, T1, to the final state B, characterized by P2, V2, T1 at constant temperature T1 along the isothermal AB. So during this process, the working substance absorbs heat Q1 from the source and it does external work W1. Since there is increase in volume, work is done by the system. Okay, so the system absorbs heat energy from the source and does some external work. And what is the work done? We have derived an expression for work done during isothermal process. So if we call work done as W1, this is going to be integral V1 to V2 PdV, and instead of P, and the final result is going to be RT1 ln V2 by V1. So we have done this derivation in the previous class, so I'm skipping the intermediate steps. If you want, you can refer to the earlier lecture. Okay. In terms of the PV diagram, this is going to be the area under the curve AB, which is nothing but area of the closed loop ABGEA. So this is the work done, and this work done is equal to the heat absorbed from the source. Okay. Next is adiabatic expansion. So here the cylinder is removed from the source and is placed on the insulating stand. So what happens? The temperature is already high here, so the gas continues to expand, but when it expands, what happens? The volume increases. So volume increases from V2 to V3. So V2 corresponds to point G, V3 corresponds to point H. So you can see volume is increasing. Consequently, the pressure decreases from P2 to P3. But when the volume increases, piston moves further up and there is a tendency to decrease the temperature, right? When volume increases, the temperature decreases. Since the stand is insulating, there is no supply of heat from outside. So as a result, the temperature decreases and finally reaches the point T2, which is the temperature of the source. So this is an adiabatic expansion and the temperature changes from T1 to T2. And if you take the initial state for this process as state B, which is characterized by coordinates P2, V2, T1, at the end of adiabatic expansion, it reaches the final state C, which is characterized by P3, V3, T2. And the process happens along the adiabatic BC. So since the volume is decreasing, here is work done on the, since the volume is increasing, once again, work is done by the system. And where does it get the energy for doing the work? From its own internal energy. Let's calculate what is the work done during this adiabatic expansion. Once again, we have done this derivation in one of the previous classes. So briefly, work done W2 equal to integral V2 to V3 P dV. And in the case of adiabatic process, PV to the power gamma is a constant, called that as K. So instead of P, I can write K divided by V to the power gamma. So apply the limits, you get 1 divided by 1 minus gamma into K divided by V3 to the power gamma minus 1 minus K divided by V2 to the power gamma minus 1. Since PV to the power gamma is constant, I can replace this K with P3 V3 to the power gamma and the second K with P2 V2 to the power gamma. So when you simplify this, you get 1 divided by 1 minus gamma P3 V3 minus P2 V2. Since we are talking about ideal gas, 1 mole of ideal gas, PV is nothing but RT, right? So P3 V3 is this point which is associated with a temperature T2. So instead of P3 V3 I can write RT2. Similarly, P2 V2 is this point which is associated with temperature T1, which means instead of P2 V2 I can write RT1. So when you take R outside and interchange the signs, you get work done equal to R divided by gamma minus 1 T1 minus T2. So this is exactly the result we had derived in the previous class. Moving on to the next process, which is isothermal compression. So here what happens is the cylinder is removed from the stand and placed on the sink. So previously the cylinder was at a high temperature T1. Now the temperature is low T2. So what happens? The gas inside gets compressed. So the piston moves downward. Okay. Now when the gas gets compressed, what happens is the volume is going to decrease. So you can see volume decreases from V3 to V4. So V3 corresponds to point H, V4 corresponds to point F. So volume is decreasing. When volume decreases, what happens to the pressure? Pressure increases. So pressure increases from P3 to P4. Now what happens to the temperature? When the gas gets compressed, the temperature inside tends to increase, but remember the top of the sink and the bottom of the cylinder both are conducting, so heat energy flows from the cylinder to the sink. As a result, the temperature inside remains a constant. So this entire process happens at a constant temperature T2. That's why we call it as isothermal compression. And during this process, the working substance changes from initial state C, characterized by P3, V3, T2, to final state D, characterized by P4, V4, T2, along the isothermal CD. And here, during the process, the working substance inside the cylinder rejects heat energy Q2 to the sink. And since the volume is decreasing, the work done is on the system. We call that as W3. So W3, this is equal to heat energy Q2. Once again, using the derivation we have done in the previous class, this is equal to integral V3 to V4 P dV, which is RT2 ln V4 by V3, or minus RT2 ln V3 by V4. Or in terms of the PV diagram, this is the area enclosed by the closed loop CHFDC. And the final process, adiabatic compression. Here the cylinder is removed from the sink and is placed on top of the insulating stand. So what happens? The temperature is very low, it is T2, so the gas continues to compress. So as a result, volume decreases from V4 to V1, and when volume decreases, the pressure increases. So pressure increases from P4 to P1, and what happens to the temperature? Since the stand is insulating, there is no heat exchange. So when the gas is compressed, the temperature increases. So it increases from T2 to the original value T1. So this is known as adiabatic compression. So during this adiabatic compression, the heat energy flows from the working substance to the sink. So let's say the working substance changes from initial state D, characterized by P4, V4, T2, to the final state A, which is P1, V1, T1, along the adiabatic dA. And during this process, there is no heat exchange. So this is the adiabatic compression, and with this, one complete cycle is done. So it starts from A, goes to B, goes to C, goes to D, and comes back to the same initial state. That's why we call this as a cyclic process. And what is the work done during this adiabatic compression? If you look at these two processes, BC and DA, they are exactly opposite. In the case of BC, I have adiabatic expansion happening here, so temperatures decreases from T1 to T2. On the other hand, in the case of DA, it is the adiabatic compression where temperature increases from T2 to T1. So the work done is going to be exactly opposite of this process. So work done W4 is going to be minus R divided by gamma minus 1 T1 minus T2. So if you want, you can do the detailed derivation, you will arrive at the same result. Now, at the end of one complete cycle, what is the total work done? Okay, so we know that during one complete cycle, the working substance absorbs heat Q1 from the source and rejects heat Q2 to the sink. So the net amount of heat gained per cycle is Q1 minus Q2, right? And what is the total work done? This is W1 plus W2 plus W3 plus W4. But as we have derived, W2 and W4 are equal and opposite. So these two cancel. So total work done is W1 plus W3. From the first law of thermodynamics, we know that dQ equal to du plus dW. But if you talk about cyclic process, the change in internal energy is zero, because we know that internal energy is the state function, right? So when change in internal energy is zero, dQ is going to be dW. So that's why in the case of Carnot cycle, the net heat gained dQ equal to the net work done dW, which means I can write Q1 minus Q2, the total heat gained, equal to total work done W1 plus W3, and substitute for W1 and W3, you get RT1 ln V2 divided by V1 minus RT2 ln V3 divided by V4. We need to simplify this. Let's try to get an even nicer expression for this. So if you look at the adiabatic dA, so if you look at this process dA, this is adiabatic compression. So we know that in the case of adiabatic process, PV to the power gamma is a constant. So we can write P4 V4 to the power gamma equal to P1 V1 to the power gamma. Right? Okay. Now, since we are talking about ideal gas, PV equal to nRT, but we consider 1 mole of gas, so PV equal to RT or P equal to RT divided by V. So in my original equation, I can substitute for P. So in the first case, the P1 V1 is associated with temperature T1, so I can write P1 as RT1 divided by V1. Similarly, in the case of P4 V4, this is associated with temperature T2, so I can write P4 as RT2 divided by V4. R is common on either side, cancel that. When you simplify this, you get T1 V1 to the power gamma minus 1 equal to T2 V4 to the power gamma minus 1, or T2 divided by T1 equal to V1 divided by V4 to the power gamma minus 1. Same way, we have another adiabatic BC. So we can write P2 V2 to the power gamma equal to P3 V3 to the power gamma. Follow the same procedure as before. T2 V2 is associated with temperature T1, which means I can rewrite P2 as RT1 divided by V2. Similarly, P3 V3 is associated with temperature T2, so I can rewrite P3 as RT2 divided by V3. If you simplify this, you get T1 V2 to the power gamma minus 1 equal to T2 V3 to the power gamma minus 1, or T2 divided by T1 equal to V2 divided by V3 to the power gamma minus 1. So I have two equations for T2 divided by T1, which means I can equate these two. So when I do that, I get V1 divided by V4 to the power gamma minus 1 equal to V2 divided by V3 to the power gamma minus 1. The power is common, so I can cancel that. I get V1 divided by V4 equal to V2 divided by V3, or when you rearrange the terms, you get V2 divided by V1 equal to V3 divided by V4. So if you remember our original expression for work done, this is the expression. So here, instead of V3 divided by V4, now I can write V2 divided by V1. So when I do that, I get the work done, which is Q1 minus Q2 equal to RT1 ln V2 divided by V1 minus RT2 ln V2 divided by V1. The ln factor is common, I take it outside, so I get work done during one complete cycle of a Carnot engine equal to Q1 minus Q2, which is equal to R into T1 minus T2 into ln V2 by V1. Once we calculate work done, we can define an important parameter of a heat engine known as efficiency, which is nothing but the ratio of work done per cycle to the heat absorbed from the source per cycle. So this is the fraction of work done from the heat absorbed in a cycle. So efficiency eta is defined as work done W divided by heat absorbed Q1. We know that W equal to Q1 minus Q2. So substitute for Q1 minus Q2, this is R into T1 minus T2 into ln V2 divided by V1. And Q1 is nothing but W1. We have derived that earlier. Q1 is W1, which is RT1 ln V2 divided by V1. So when you substitute for these two, you can cancel the common logarithmic term and also the common factor r, then you get efficiency eta equal to T1 minus T2 divided by T1, or 1 minus T2 divided by T1. There are a few important inferences from this equation. First one, as you can notice, efficiency is independent of the nature of the working substance because there is no material parameter involved here. And second one, what is the maximum efficiency? Can I have 100% efficiency? If efficiency is 100%, then eta equal to 1. So what are the cases in which eta becomes 1? First one, T2 being 0, right? So 1 minus 0, 1. Okay. Now, is it possible to have zero temperature? Remember, we are not talking about degrees Celsius, we are talking about Kelvin. So we know that it is practically impossible to reach absolute zero. So efficiency of a real heat engine is never 100%. What is another possibility for eta being 100%? T1 equal to infinity. So you divide anything with infinity, you get 0, right? Now once again, it is not practically possible to reach infinite temperature. You can reach very high temperature, but infinite temperature not possible. So once again, the efficiency of a real heat engine is never 100%. Now, in the case of a Carnot engine, we have discussed in the last class that there is an important assumption that all the processes happen quasi-statically, right? Quasi-static means infinitely slow, but no practical heat engine can work infinitely slow. In fact, they all work very, very fast. So it is not possible it's not possible for a real heat engine to have efficiency higher than a Carnot engine. In other words, among all the engines, Carnot engine has the highest efficiency. Now, if you have a practical heat engine, how do you increase the efficiency of it? So looking at this equation, we know that the factor T2 divided by T1, this is the decrement factor. So if you decrease this factor, then you can maximize the efficiency. Now, how do you decrease this factor? Either you decrease T2, so keep the sink temperature T2 as low as possible, or you can increase T1, so keep the source temperature T1 as high as possible. But typically in any practical heat engine, the sink is the surrounding air, which is always at the room temperature, so it's difficult to decrease the sink temperature below room temperature. On the other hand, you can increase the source temperature. That's why if you look at the old heat engine, they used to work on coal, but most of the modern heat engine work with petrol or diesel, because when you burn petrol or diesel, you get a much higher temperature compared to a burning of coal. So that's about working of a Carnot engine and how to analyze its working using the indicator diagram. But you may be wondering, how does it relate to any of the practical engine? For example, when you drive a car or a bike, there is a heat engine inside it, right? And what is the working of that heat engine? Okay. So I will give you a glimpse of a 4-stroke engine, which is commonly used in bikes. So if you are aware, the old generation bikes used to have a 2-stroke engine. Most of the modern bikes have the 4-stroke engine. So I'll give a brief summary of the working. So as you can see, there is a cylinder here, and inside the cylinder there is a piston, just like the Carnot engine, right? And there is a crankshaft here. So if you look at the piston moves up and down vertically. So this is a linear motion. But for a vehicle to move, for its wheel to rotate, we need a circular motion. So it is the crankshaft which converts the linear motion of the piston into a circular motion. Okay. Now, Each movement of the piston, whether upward or downward, one single movement is known as a stroke. So here one complete cycle has 4 strokes. Piston comes down, goes up, comes down, once again goes up. So that's why this is known as a 4-stroke engine. So here you can see there are 2 inlets, one for air and one for fuel, and usually the working substance is a mixture of air and fuel, because as we all know, for fuel to burn there must be an oxygen supply. That's why we mix air with fuel, and typically the ratio is fixed. It's around 14.7:1, which means for 1 kilogram of fuel 14.7 kilogram of air is needed. It may vary slightly depending on the particular make of the engine. And there is another exhaust valve. So in the first stroke, what happens is the inlet opens, so a mixture of air and fuel goes inside. Okay, so the cylinder is filled with air and gas mixture, which is the working substance. Now in the second stroke, what happens is the piston moves upward. So here the inlet is already closed, so when the piston moves upward, the working substance gets compressed, so there is high pressure inside. In the third stroke, what happens is there is something called a spark plug here, which generates a spark. So you have high pressure fuel inside, so when spark comes there is an explosion as indicated by this red diagram. Okay, so when the explosion happens, suddenly a large amount of heat is generated, so the gas inside expands, so the piston comes down. That is the third stroke. And finally in the fourth stroke, what happens is the exhaust valve opens, so all the exhaust gases goes outside. As a result, the piston moves up. So you have 4 strokes. In the first stroke, the working substance enters inside the cylinder. In the second stroke, the working substance is compressed. In the third stroke, there is a explosion generated by the spark plug. In the fourth stroke, the gas leaves out the cylinder through the exhaust valve. So I have 4 strokes, and if you look at the fourth stroke, the power is generated only in the third stroke, right? That's where the explosion happens and the piston move downwards. So power is generated in the third stroke, and the power generated in the third stroke drive all the other 3 strokes. Okay, so there is a continuous movement of the cylinder up and down, and through the crankshaft this continuous linear motion is converted into a continuous circular motion, and this is connected to the wheels of the vehicle, and as a result of this the wheels move. So usually the crankshaft moves at a speed of thousands of rotations per minute. That's we call as RPM of the vehicle. And also there is another important parameter known as CC. Probably you would have heard about 150cc bike or 200cc bike. CC refers to the volume of the cylinder, usually the volume through which the piston moves. So you see the piston moves up to this point and it comes down up to this point, right? So this volume is referred to as the CC. CC means centimeter cube. Okay. So these are some of the parameters associated with a working engine, and briefly this is the working of a 4-stroke engine. So if you want to understand more about working of practical engines, you can go to YouTube. There are hundreds of videos available. One good video reference is given in this link. So this explains the working of a 4-stroke engine in Malayalam. So if you want, you can watch this video. It's very informative, and the working of a 4-stroke engine is explained in a lucid manner, because it's important that we understand some of these practical aspects, especially if you are a driver, if you are familiar with driving. Understanding the working of an engine helps you to use your vehicle more effectively. You can maximize the fuel efficiency of the vehicle Also, if you understand the working of the engine, you can keep it in a good working condition, which also decreases your maintenance charges. Also, as students of thermodynamics, it's important that we understand the practical working of engine, because it's important to know the theory of all this, but more important is how does the theory get translated into practical action. So that's for today. In the next class, we will see what happens if we operate a heat engine in the reverse direction. Like so far we have discussed heat flow from the source to the sink, right? That is the normal course of action for a heat engine. What happens if you reverse the direction, if heat flows from sink to the source? So this is the working principle behind a refrigerator. So in the next class, we will discuss more about the working of refrigerators. Thank you.